So this is question 35 from paper 12 that was administered February, March 2019. And the question reads, a wire of cross-sectional area 5.0 by 10 to the negative 6 meters squared is made of a metal of resistivity 50 by 10 to the negative 8 ohm meters. The potential difference across the wire is 6.0 volts and the current is 3.0 amps. What is the length of the wire? So there's a lot of information contained here. And a strategy that sort of I like is, I mentioned it before, sort of what's the equation that allows me to solve my final answer? And so the way that I sort of remember the equation is resistivity is RA over L. And so L, the length of the wire, right? That's this. And so I know kind of that's what I want to solve for. Let me multiply both sides by L and divide both sides by rho. And then I've got this equation, L equals RA over rho. I can see that they've given me the area A, so that's kind of nice. I've got that. They've given me the resistivity rho. It's kind of nice. I've got that. And the resistance is not given, but they must have given me some information to solve it. They're not going to give me an impossible problem, right? So how do I calculate R, the resistance? Well, resistance is voltage divided by current. Potential difference, that's voltage, right? And so 6 volts divided by 3 amps is 2 ohms of resistance. And that's sort of the final piece of the puzzle, right? So now I can go back to this equation for L. L is equal to 2 ohms of resistance, right? So because resistance is the ratio of voltage to current, right? It's kind of the way you might answer the essential question today. How are voltage and current related to resistance? Well, resistance is the ratio of voltage to current, right? That's sort of this one that allows us to deduce the resistance. Here is 2 ohms. The area is given 5 by 10 to the negative 6 meters squared. The resistivity is given 50 by 10 to the negative 8 ohm meters. Oh, that's a bad looking omega, my bad. Cancel out that, especially that omega that's right there, right? And then cancel out one of those, and I'm left with meters of length, right? The units are always good to sort of check and make sure, like, solve it for length, that's it, meters, and I do, right? Kind of cancels out. And so now it's just crunching the numbers. 2 times 5 times 10 to the negative 6 divided by, open parentheses, 50 times 10 to the negative 8 equals 20. All right, and the moment of truth is when I click on this tab, the mark scheme. We look at question number 35, and we're looking for D. Okay. Question 35 is D. Good feedback. We'll take a look again. D is 20 meters. Good. All right, last question, and this segues us into our lab work. Which graph shows the variation with current I of the potential difference V of a filament lamp? Now, this isn't something that we've studied yet, and so it's just one I want to discuss. I don't expect you to even attempt to answer this. In fact, I would encourage you not to. First of all, look that it's not an IV characteristic like I've got on the board. An IV characteristic is only put current on the vertical axis. This is just voltage against current. It says you can't plot your data that way. I'm just telling you, when you look up in the literature about like what's the IV characteristic of sort of anything, it's that. It's I against V. It's called IV characteristic. But that doesn't mean we can't sort of look at data this way. For things that are metal resistors that obey Ohm's law, I mean, look at the equation. Voltage and current are proportional. It gives us sort of one value of resistance. And so a metal, resistor looks like this. Okay, that's what its curve looks like. A filament lamp is not a perfect metal resistor. And in fact, it's what we call a non-ohmic component. And we'll study other non-ohmic components. In other words, they're components that don't really obey Ohm's law everywhere. Just like Hooke's law. Remember the way we thought about Hooke's law? It's like when the extension is proportional to the force, that's when the material obeys Hooke's law. But there's a point, an elastic limit, that we could sort of overwhelm the elasticity and no longer obeys Hooke's law. So if we think about like this curve right here, this would, so if this were, let me sort of change it. D is not the correct answer, but if it were an IV characteristic, if this were I, and this were B, then this would be the right answer. So an IV characteristic, that's what it looks like for a filament lamp, okay? So it kind of obeys Ohm's law here, right? Like here it basically is proportions. Like we could get like a slope there, right? And the inverse of that slope would be R. Remember how we talked about how like the slope of this is V over I, or I's over run. Like that would give us R, right? The slope of this. But if it's I against V, remember we got to take the inverse. So this part kind of obeys Ohm's law, but then there's a point where we increase sort of the voltage more, and we don't get the corresponding increase in current, right? It starts to sort of level off. So like even if we increase the voltage a lot, we're not getting any more current through it. And the reason why is because of what a filament lamp sort of does. It's designed to get hot and low. And so, the energy doesn't go into current, but into sort of heating it up. Okay, and so it stops sort of obeying Ohm's law out here. No longer, is the voltage and current proportional. So the correct answer to this question, because we aren't looking at an IV characteristic, is like the curve would look like this, where it starts to trail off like that. And so that just sort of means it's going to look like this on a V versus I plot. So A is the correct answer here because one, it's not a metal conductor. In other words, the word filament lamp, a student of physics would connect that with non-ohmic component. It's not going to be a straight line. It's going to be a curved line. And if we're looking at V against I, it's going to curve sort of up this way. So that with an increase in voltage, right here, we're increasing the voltage a lot, right? Like there's a big jump in voltage. We're not really increasing the current in proportion anymore, right? Like the voltage goes up and up, but the current's like, I'm not going anymore. That's as much current as you can get out. And so A is the correct answer if we're looking at it that way. It's the same thing if we were to sort of, just reverse these axes, then the curve would look like this. And so you'll see on an IV characteristic of a filament lamp looks like this. Okay, that's the IV characteristic. It can go, sort of this way. All right. And so filament lamp, again, non-ohmic component. It does not obey Ohm's law sort of everywhere. All right, let me see if I can move over with the hover camera to my lab station here. So I'm going to disconnect the Wi-Fi, disconnect my writing tool, stop my screen share. I wonder, still project though to you all, because it's like I go to the corner of my lab to find a good lab station. Lab bolt there. On my writing here. Do that. All right, let's see if this works. Here's my resistor. Okay, you can see I've got it wired up there, and I want you to tell me what is the value of that resistor. It's hard to see, but here's the lab volt station right there. It's autofocus now. All right, so the lab volt station, I've powered it on, and I've got, it's a sort of a low voltage power supply, so I can vary the voltage by twisting this knob right here. This one is, these are multimeters, so they measure multiple things, okay? And this one is set up as a voltmeter right now, so it's on a range of 20 volts. And this one is set up as an ammeter, and it's actually on a very high range. It's on a 10 amp range, okay? Trust me that I've wired it up correctly, okay? It's really tough to see where it's like, different connecting leads, but I basically have coming out of the wall of the source of EMF going into my ammeter, right? Because this has to be part of the circuit. And then it comes out of the ammeter into my resistor that's sort of out of the frame right now. Okay, and then out of the resistor back into the wall. The voltmeter is wired up in parallel. So voltmeters have to be wired in parallel. You know what I was supposed to do? I thought about this. Oh, we should sketch this circuit before I go over. Work through it. My document camera used to be on this little cabinet here. If I ever worked on it, I'd have like my back to the students doing work like this. Y'all paying attention to it? Oh, so eventually I was just like, forget this one, put it right here on my desk. Right? So it's like, this reminds me of like, let me do my work here with my back to the students. But you don't see everything going on right there. All right, so where are we over here? So here's the circuit we've got. We've got a source of EMF. Okay, remember that that's the symbol for that. And I've wired up to it a voltmeter in parallel. So the symbol for a voltmeter kind of looks like this. So here's the circuit that you can kind of sketch for this week's lab. We got a voltmeter in parallel with the EMF. And then I've got a ammeter in series with a resistor. Kind of like that. So here's my voltmeter, and it's in parallel, okay, with my EMF source. Remember, the EMF source is this guy down here, right? So there's the EMF coming out of the wall. It's like a plug. And I'm going to vary the voltage by adjusting that. So this meter, which is set to volts, that's going to be the voltage. That's this one, okay? So this is this component. The ammeter here is wired in series, right? So it's coming out of the EMF, and then this is just like part of the circuit with the resistor. The resistor, again, is up here, okay? So we have a resistor. I want to know what is the value of this resistor. That's going to be the claim on which you'll report. How are you going to do it? You're going to plot the data. And I don't care if you plot V against I or I against V. I just want the conclusion to be correct. Hopefully that makes sense. Like if you plot V against I, your conclusion will be what? The slope. You just take the slope of it because R equals V over I. If you're like, well, I want to practice IV characteristics. Dr. Schleich told us that, textbooks tend to present the data like this, IV characteristics. And we'll study that. We'll see plenty of that like in this course. And so if you want to practice an IV characteristic, plotting an IV characteristic, then you need current on the vertical axis. So you just change your X and Y coordinates, right? And then the slope calculation, you take the inverse of it. So it's not the slope of this that gives the conclusion, but 1 over the slope. So, and change it to run over rise, and then you'll have the answer, right? So R equals, the change in the horizontal axis over the change in the vertical, right? So it's up to you, how you want to sort of interpret your data. Let's go ahead and get some numbers. All right, and see, like the thing about the multimeters here. This multimeter, the ammeter, it's set to the 10 amp range because the other sort of, the next lowest range is measures up to 200 milliamps. And you actually need to disconnect sort of this the red lead here, it's in like a special 10 amp port. So it's like high current, you know, there's like a special sort of setting for that where you just literally have to unplug it, plug it in here. We'll quickly exceed the range 200 milliamps, you know, with the voltages that we can sort of achieve here. Like, and then this thing will say OL, overload. And so rather than like unplugging it and plugging it back in, I said, well, we'll just like sort of measure everything on the 10 amp range, and we won't overload it hopefully here, but we would have to like sort of change it. And, you know, time permitting, maybe we'll see that. So let me go ahead and increase the voltage here. So we should see this number increasing, that's the voltage. So as the volts go up to, as the volts go up, the amps are doing nothing, which is not good. All right, let's try this again. So here I've readjusted it, so you know it's just a little bit more sensitive now. I kind of have a feeling that I damaged the multi. So we're seeing some kind of current being read there, but I have a feeling that we're either have a bad wire somewhere. So this is coming out of here. That's the voltmeter, good. This guy. Okay, that seems good, good. So this morning I kind of tested it just to make sure, and you end up putting a lot of current through it when you ramp up the voltage a lot. And I think I might have fried the circuitry, or maybe something else. That's the troubleshooting with circuits. It's always that, but my circuit's not working. What's wrong? It's like anything could be wrong. Batteries are dead. The wires, you know, the guy just can't get full. I'm suspecting a bad ammeter. I'm going to replace this guy. And so this thing is wired right here. And right here, these two. Get this guy out of here now. All right, so here is my ammeter, and I want connected like this. Which makes me suspect that it wasn't a bad multimeter, but something else is bad here. This is the fun. See, it's a box of working multimeters, which means I've got a box of not working ones. Sometimes those boxes transfer. just getting nothing. We're getting a voltage, but no current. So change my resistor out. Maybe that's what got dried this morning. And the same thing might happen too. Because I was like, oh, we're getting really good data here. Should have recorded that. You know, because like as I'm increasing this is increasing, good, and then the current just starts to decrease down to 0. Like, whoa, I quickly turned it off, hoping like maybe nothing's wrong. But yeah, maybe I fried the resistor there. All right, let's see here. So we'll get rid of this guy. Here's another type of multimeter. Maybe we'll have better luck with it. There we go. All right. All right, let's get some data while we can. 0, 0 is a data point. So you got a data table, voltage measured in volts. That's this one, the red one. Amps of current. I, intensity of the current, I measured in, this is going to be milliamps now. Okay, so see, I have it set to the 200 milliamp range. The way to sort of read these multimeters is, see, I've set it on amps. So this is like alternating current voltage. This is direct current voltage. So it's a voltmeter, it's an ohm meter, it's an amp meter. It's a multimeter. Measures all those things. These different values are the range. So it can measure like up to 2000 microamps, up to 20 milliamps, or up to 200 milliamps. I've got it set to 200 milliamps. In order to get to this 10 amp range, I need to disconnect this red lead and plug it in here. You see how down here it says 10 amp max. Okay, so that's a special port just for high currents, like 10 amps. So we have 0, 0. I'm going to increase the voltage. As the voltage goes up to 0.3, the current increases to 2.4 milliamps. So 0.33, 2.4. I saw those numbers together. And if you see a set of numbers up there that's slightly different, you know, record them. That's empirical data, right? There's nothing wrong with it. I'm going to continue to increase the voltage. The voltage is trying to get it right around 1. So 1.03, 27.1.02, 27.5. 1.02 volts, 27.5. Remember, milliamps is what we're measuring. So it's lowercase m a. I want to start over. Sorry, everybody. I really should be recording this. Oh, I am recording. Awesome. I've been recording the whole time. So I've got all of my mistakes and all the frustration there too. All right, where were we at? About 1. Let's try to crank this guy up to about. When the voltage is 3. See, I'm really right at the edge of that 200 milliamp range. You see how it's almost overloaded? And that 1 means it is overloaded. So let me just back it down. 2.85 volts, 198.9, 199.1. Pick a number there. See, it's right at the, you know, almost overloaded. 2.75, 196.0. Okay, now here's where I'm going to have to change this to the 10-amp range. Disconnect this red port here. Get into this guy. That. And so now, see how it just moves a decimal point. So now see how it's above 200 milliamps. It's amps now, but it's 0.24 amps. So what's that? That's 240 milliamps. It's 0.24 amps. So 2.44, 240 milliamps if you want to keep milliamps, or you can change it to amps now. But we need to plot everything together, like plot everything in milliamps. So it might be easier to say, well, this is 240 milliamps, right? 0.24 amps. All right, let's jump the voltage up. To 4.4. 4.779, 4.82, 0.47. So 470 milliamps at a voltage of 4.8, 460 milliamps, 4.8, 470, somewhere around. See how it's a little bit touchy. And again, it's like all the contacts here. You can kind of see like all the places where these are not perfect sort of contacts, and it's measuring sort of the charge here through and the voltage across it. All right, let's crank it up. .9. So at least this one you can do this. Hold 6.96.68. It's like I can hold the value in there if it's really jumping around, but you do kind of want to see like, well, did something drastically reduce the voltage? Like, you just hold it there, just sort of keeps it up. So 680 milliamps, it seems to be sort of around 6.8, 6.9 something. You choose your favorite number within that range. It's like, hopefully the conclusion, isn't too bad. But that's sort of when we talk about the random error, right? Like there's a bit of scatter, but it's generally sort of around this. So what we're getting is a trend. We're definitely, as I'm increasing the voltage, this is going up, right? We haven't violated that trend, and so that's good. 9 volts. I've almost got 1 amp. I got 0.95 amps, 950 milliamps, 940, 950 milliamps, somewhere in there. So at 9 volts, I'm almost at 1 amp. Okay. Well, I think I saw 1 there. And wow, that jumped up to 13, 14, and look, this crashed to 0. So that's what I think happened this morning, is that I've got so much voltage now, 16, 18, 19 volts. This is like the max, that like I'm sure these wires might be getting hot right now. I don't know. But yeah, see how it just crashed? Like I probably broke this multimeter. 1 day left to retire. How many data points do we get? Enough?